Hi guys, Mr. Rocco again. This will be the last video on astronomy, this unit, topic 3. And then again next week there'll be an astronomy quiz on Castle Learning, so you're going to look for that. Let me get right into this. This is on stellar evolution, stellar meaning stars, and how they evolve, the life cycle of a star. So this diagram shows our sun. From birth till the end. This is where we are now. We are at about 4.6 billion, with a B, billion years old. Our sun, our solar system, is 4.6 billion years. Don't confuse 4.6 with the age of the universe. The universe and the Big Bang started around 13.7, 13.8 billion years ago. So you had Big Bang, universe 13.8 billion years ago, and then it took 9 billion years until our sun came along. Anyway, so this just shows this diagram here, 1 billion years, 2 billion, 3 billion, 4 billion, 4.5. Here we are. When we get out to about 10 billion, roughly. So we still have another, 1, 2, 3, 4, 5 billion years to go, roughly. This is what's going to happen to our sun. You might say, Mr. Rocco, how did they know that? Studying other stars, similar stars to our sun. Our sun is not the biggest, it's not the smallest, average size, average temperature. So looking at other stars like our sun, they've seen them go through this process already, and so they know what's going to happen. And so our sun, which is yellow, will eventually expand the outer shell to become a red giant. At that point, probably Mercury, Venus, and Earth probably will also. It's kind of Earth's on the fence, but if it doesn't get completely swallowed up by the red giant, the oceans will evaporate, the planet will become super hot, and life as we know it will cease to exist. So even if the planet isn't completely swallowed up by the red giant, that'll be it for Earth. After that, this outer shell, the red giant of the shell, the outer shell will kind of dissipate and kind of blow off, left with a small white core, becoming what's called a white dwarf. White is hotter than yellow. I'll get into that HR diagram as a chart in your reference table toward the end of this video. Anyway, so it'll be a hotter star, but it'll be a smaller star. But again, Earth will kind of end right here at 10 billion. And you can see by the time we're a white dwarf, we're talking 13, 14 billion. So it's going to take a couple of billion years to go through the dying process. But unfortunately for Earth, Earth's days will end at 10 billion. So we've got, again, like I said, a little over 5 billion years to go. Stars are born out of what's called nebula. Nebula are huge clouds of dust, gas. They collapse under the force of gravity. Gravity being one of the primary forces when the universe was formed. And so you've got these huge dust clouds that collapse under the force of gravity to form what's called a protostar. Proto means new stars, like cars. So if you follow when they make new cars, the first car they'll make is called a prototype, right? New type. And then they'll mass produce them on an assembly line. So a protostar is a new star. Young stars, younglings. These young stars undergo further collapse, forming what's called a main sequence. And we are a main sequence. Even though we're 4.6 billion years old, we're still in the early stages, so to speak. But anyway, stars come from nebula, dust clouds. Stars expand as they grow older. Again, you saw I showed in that diagram, we're going to become a red giant, so we're going to kind of swell up. It says, as the core runs out of hydrogen and then helium, the core contracts, the outer layer expands, cools, and becomes less bright. This is a red giant, so that's what's going to happen now. So red is cooler than yellow. We're a yellow star, right? In kindergarten, you color it yellow. We will expand but cool and become a red giant. Eventually, the core will collapse. The outer part will kind of explode away. Its fate is determined by the original mass. So average sized stars like our star, we don't go out with a huge bang. We don't become black holes. That's saved for the big stars. So the bigger the star, the giants and the supergiants, they go out with a supernova. These huge bright explosions, or they swallow themselves up completely and become a black hole, and kind of collapse on themselves tremendously. Our sun will become a white dwarf and eventually lead to a black dwarf. It says the late stage of stellar evolution is black dwarf, 2 to 3 degrees Kelvin. Now 0 Kelvin is a special number. That's absolute zero. At absolute zero, all molecular motion would stop. Like nothing would move. Temperature-wise, in Fahrenheit, it's around negative 470 degrees below zero. So when you're talking 2 to 3 degrees Kelvin, I mean, you're basically in the 400 below zero range. Extremely cold. It says because they emit no heat and no light, these objects would be a challenge to detect if they exist today. However, at less than 14 billion years old, the universe is still too young to have created any black dwarfs. So white dwarfs, yes. Black dwarfs, no. A main sequence star that lacks the mass necessary to explode into a supernova and will become a white dwarf, a dead star that has burned through all its hydrogen and helium fuel. But the white dwarf remains hot for some time, much like a stove burner still gives off heat even when it's been turned off, right? If you have an electric stove, or I have an electric smooth top stove, you shut the heat, you can turn the dial off, right? It's off, but the top of the smooth surface is still hot, right? And that's kind of the same idea. After enough time has passed, all the leftover heat will have radiated away. No longer emitting heat or light, the white dwarf will again become a black dwarf, its loss making it difficult to find. However, the black dwarf would still retain its mass, allowing scientists to detect the effects produced by its gravitational field. So that's really what they're going to be picking up. You're not going to see them, right? They're black amongst a black background in the sky, in the universe. But they're going to pick up the gravitational pull of that black dwarf, is what they're saying. Neutron stars are thought to form by this gravitational collapse of the remnant of a massive star. So we're not going to form a neutron star. That's safe for the big guys, the supergiants. This will happen after an explosion, after a supernova. Neutron stars pack their mass into a 12.4 mile diameter. Now you got to remember, these supergiants, they're, huge. I don't know what other way to put it. Way bigger than our sun. Our sun would be a speck compared to some of these supergiants. They take all that mass and pack it into 12.5 miles. They are so dense, a single teaspoon of a neutron star weighs 1 billion tons. All right, a ton is what? 2,000 pounds times 1 billion. That's how much in a teaspoon of this mass. Incredible amount of density. On average, gravity of a neutron star is 2 billion, that's what it'd be, 2 billion times stronger than the gravity on Earth. So these are just unbelievably strong gravitational pull in these neutron stars. But again, that's going to happen to the massive stars, the big guys, not us. Stellar evolution is the process by which a star undergoes a sequence of radical changes during its life. Depending on the mass. Mass is the critical part here. This lifetime ranges from hundreds of thousands of years, which you might say, well, that's a long time, but in the world of a star, a couple 100,000 years is quick, to billions of years, tens of billions, hundreds of billions of years. So depending on the mass. Mass is the critical part there. Stellar evolution begins when a GMC, not the truck, not the car company, a giant molecular cloud, GMC, again, a huge nebula, also known as a stellar nursery. Most of the empty space inside a galaxy actually contains 1/10 to 1 particle per cubic centimeter, but inside these GMCs, these giant molecular clouds, typical density is a few million particles per cubic centimeter. A GMC is between 50 and 300 light years across. If you recall when we did light years, 1 light year is equal to 6 trillion miles. 6 trillion is 1, So these nurseries are 50 to 300 light years across, and they have 100,000 to 10 million times as much mass as our sun. As the GMC orbits the galaxy, one of several events might occur to cause its gravitational collapse. A GMC may collide with each other, so you can get two GMCs and they collide, which then triggers, right? You could have a star forming party. A nearby supernova explosion can also trigger, sending shocked matter into the GMC at very high speeds. And finally, galactic collisions can trigger massive bursts of star formation as gas clouds in each galaxy are compressed. So, yeah, that is true. Galaxies do collide. Galaxies do combine. And so there's a bunch of ways that you can trigger star formation. Again, you can have these GMCs colliding with each other. Stars sometimes form when there's another star that explodes. So you could have a huge star out there, one of those super giants that explodes in a supernova, sends out shock waves, hits one of these GMCs, these molecular clouds, that causes it to collapse and to start forming new stars. So it's very ironic, I think, that you could have a star die and then trigger baby stars, protostars being born. So you could have one star being exploding and dying, but yet triggering the kickstart of other stars. Kind of ironic. As the GMC collapses, GMC fragments break into smaller pieces. In each of these fragments, the collapsing gas releases gravitational potential energy as heat. As its temperature and pressure increase, the fragments condense into rotating spheres of superhot gas known as your protostar. So all of this is the formation of a baby star. You've got these. It's all about gravity collapsing, temperature increasing, pressure increasing. Everything's starting to get hotter and more dense, and then there's a rotation that starts, which creates the protostar. New stars come in a variety of sizes and colors. They range in spectral type, from hot stars, which are blue, to cool stars, which are red. This is not common sense. If you're looking around your house and you have a kitchen faucet, bathroom faucet, normally the red handle means hot water and the blue handle means cold water. Well, actually, that's the wrong way in the world of colors and stars. Blue actually means hot. Red means cold. And I believe I've had some students, I personally can't say I've been, but I've had students that have said, hey, I've gone to Europe, some countries in Europe, where you might stay at a hotel in certain countries, and that's how the faucets are. And don't quote me on that because I haven't been to Europe. Maybe some of you have been to Europe, where the red handle actually is the cold water, and the blue handle is actually the hot water. I always think of a flame, especially on a propane torch. The deep blue part of the flame is always the hottest part. The red part of the flame actually isn't as hot. I'm not saying stick my finger in the flame. It's still going to burn. It's still going to hurt, the red. But temperature-wise, the blue, or the deeper the blue flame, the hotter it is. And so in the world of stars, that's exactly how it works. Blue stars are hot. Red stars are cold. Now, this should be familiar to you when we talked about the red shift, right? Big Bang. Everything started as one large clump of material and then expanded outward. Well, expansion is a cooling process. When you move things away from the center point, air, let the air out of a tire, let the air out of a balloon. The air is expanding. We'll get into that more when we get into the weather. But air that expands cools. And so as the universe expanded and then everything spread out, stars started shifting toward the red. They moved away from each other. They started to get colder, not hotter. So the universe, again, in the beginning was extremely hot, millions and millions of degrees Fahrenheit. Since then, all this time, 13 billion years later, plus 13 plus, it's expanding and cooling. That's a red shift. So you're noticing more stars shifting to the red, and that's because of that Big Bang, that expansion. The brightness and color of a star depend on its surface temperature. So what color it is depends on the temperature, right? Blue is hot, red's cold. which in turn depends on the mass. A new star will fall at a specific point on the main sequence of what's called the Hertzsprung-Russell diagram. Hertzsprung and Russell were two astronomers that created this diagram. This is the diagram. I'm going to show you a short video on this. It's on page 15, the top of page 15 in your ESRT. And I'm going to show you that video in a minute. Small, cool red dwarfs burn hydrogen slowly and will remain on the main sequence for hundreds of billions of years, while massive hot supergiants will leave the main sequence after only a few million years. So there's a short time. A mid-sized star, like our sun, will remain on the main sequence for about 10 billion. Again, we're on there, and that was that timeline I showed you at the beginning of this video. We've been on for about 4.5. So another 5.5 billion years where we're going to stay main sequence, and then we start to move away from the main sequence and off that part of the chart. And I'll show you that. The sun is thought to be in the main sequence, thus it's on the, be in the middle of its lifespan, thus it's on the main sequence. Once a star expends most of its hydrogen, again, hydrogen is the fuel. We go through that process called nuclear fusion. A few students on the, I think it was an assignment last week, yeah, that astronomy review worksheet, and it said, what's the process that stars use to make energy? It's not fission. Fission is splitting of the atoms. I'm going to fuse them together. I'm going to take hydrogens, and they're going to smack together. So I could have a hydrogen here, right, and I can have another hydrogen, and this happens at billions and billions of them per second. The rate in a star is amazing. They're going to smack together. That's called nuclear fusion. So they're going to combine, not split. So be careful with those questions I gave you like that last week's assignment. It's fusion, not fission. Anyway, once a star has gone through all of that fusion process and there's no more hydrogen, it starts to move off that main sequence and starts to go through the dying process. After a star has burned all of its fuel, its remnants again can take one of three forms, again depending on the mass. Mass is the critical part. Low mass stars, which would be us, we're not a giant, we go into that white dwarf. So again, if you remember that timeline I showed you at the beginning of the video, right? We end up being a white dwarf, which eventually leads to a black dwarf. The bigger stars, like the medium stars or the big supergiants, they are the ones, again, that become those neutron stars, right? With that immense, a teaspoon was, right? Huge density there, billions of tons, or they go into a supernova explosion. And again, so the massive stars are going to be the ones that go out with these huge supernovas or black holes. The low mass stars like our sun, white dwarf, kind of fizzle out, I guess. So this just shows a similar chart, except it's got bigger stars too. So again, you always start with that stellar nebula, that little nursery. This would be your GMC, Giant Molecular Cloud, and then it triggers a protostar. Here's our sun at the top. So we're average size. When we get to the end there, at 10 billion years, so 5 billion years from now, that's when we expand, red giant, the outer shell blows off. We're left with that white dwarf, and I could even add on here, there'd be a black dwarf somewhere on the other end here, at the end. The bigger stars, right, they're going to also become supergiant, but they're going to have so much more mass to them, they're going to explode into a supernova, which will then lead either to that really dense neutron star, or, like I said, they kind of create their own black holes. And again, our star will not become a black hole or supernova or neutron. All right, here's the chart. I'm going to put this video up for a second, then I'll talk a little bit more about it. So let me share this. This guy, I use him a lot. He's a earth science teacher out in Western New York. He's taken the reference table and he's broken every chart down into little short videos. And rather than reinvent the wheel and make my own video for these charts, I'm going to let him do the explanation. I'll come back and maybe touch on a few things, but let me pull this up.
Hi everyone, welcome to the Earth Science Regents Review podcast series created by Homix Middle School Earth Science Department. Today we're going to focus on page 15 in the reference table, the characteristics of stars chart. Now this chart organizes our stars based on a couple different factors. One of the factors is going to be luminosity, how bright a star is or how much light a star is going to give off. That's going to be along our vertical axis. Our horizontal axis, there's two scales. Temperature in degrees Kelvin, that's going to increase from right to left across. So stars on the right-hand side tend to be very cool. Stars on the left-hand side tend to be very hot. Now each temperature is going to correspond with a color. Your red stars tend to be very cool. Your blue stars tend to be very hot. On the right-hand side, just gives you a little scale in terms of size. Small stars are going to be on the bottom. Big stars are going to be on the top. Now, many stars are going to be organized by mass and by size. That's where a lot of our stars are going to fall into those categories. So we have supergiants, which are an intermediate stage. They're kind of middle-aged stars. We have giants, okay, which again are middle-aged stars. We have white dwarfs, which are late-age or very old-age stars. And we have what are called main sequence stars. Okay, those are going to be the early-age stars. And that's actually where our sun is actually going to fit into that category as well. So one thing that happens quite a bit is comparing stars. So you need to understand surface temperature, color, and luminosity in regards to your stars in this chart. Let's show you how this is going to be used. So for instance, our sun has a temperature a little bit less than 6,000 degrees Kelvin, and our sun has a luminosity of 1. Okay, luminosity of 1 is an arbitrary number given to our sun. Any numbers bigger than 1, okay, such as 10 and 10,000 for instance, just tells you how many times brighter a star might be. So for instance, the number 10 represents 10 times brighter than our sun. 10,000 represents 10,000 times brighter than our sun. But you also have numbers less than 1, which represents how many times dimmer. So for instance, stars that have a luminosity of 0.01 are 1/100th as bright. They're significantly dimmer than our own sun. So if you take, for instance, Polaris. Polaris is going to have a luminosity of about 6,000 degrees Kelvin. That star is going to be about a yellow star, okay, and is going to be somewhere in the neighborhood of about 5,000 times brighter than our own sun. You can get a star like Eridani B. Okay, Eridani B is going to have a surface temperature somewhere around 18,000 degrees Kelvin. It's definitely going to be a blue star, okay, but it's going to have a luminosity about 1/100th as bright as our sun. And a lot of times our brightness of stars is going to correspond with the actual sizes. The bigger stars tend to be brighter, the smaller stars tend to be a little bit dimmer. Okay, so very important to be able to identify, okay, your stars in relation to luminosity, surface temperature, and color. So that's pretty much about it for this chart. See you next time.
Okay, close that. So if you heard what he was talking about, so let's take our sun again. The hardest part about this chart is this temperature scale. Again, if you think of a graph, usually you start 0 on the left corner and then you increase as you go to the right. This does the complete opposite, so be careful. 2,000 is the coldest star. 30,000 is the hot stars, the blue stars. So it goes colder from the right. It increases as it goes left. So that's opposite of a graph. Graphs usually go higher as you go on the x-axis, increase as you go to the right. This increases as you go to the left. So you have to be very careful. And that's why he was talking about the sun, right? If I take my straight line tool here, take that little plus where the sun is and come straight down, what'll end up happening, and they're going to try to trick you on the regions because they know kids are going to make the mistake and say, oh, it increases as you go this way. So you see right here is 2,000, this is 3,000, 4,000, 5,000, 6,000, 7,000, 8,000, 9, 10, 20, 30. So when you look at this sun come down, you'll say, kids will say, oh, Rocco, it's a little bit more than 6,000. They'll call that like 6,200. But again, the problem with that is, see, it's colder to the right, not warmer. So you're going to actually be not above 6,000, you're going to be lower than 6,000. So the actual, and this is surface temperature, the actual surface temperature of the sun, I would call that 5,800. You're not 200 above, you're 200 below Kelvin. So it's 5,800 Kelvin, because this is 4, 5, 6, right? It's increasing as I'm going to the left. So just be very careful. That's a very easy mistake to make. And kids go, I I read it the wrong way. I'm so used to graphs increasing as you go to the right. Yep, this goes the other way. So just be very careful. Color goes with temperature. So again, if our sun's here and I come down, right, and I go past the temperature scale below it, you can see you're right in yellow, right? Go straight line down, there's yellow. And that's why in kindergarten you colored it yellow. If I take a star like Proxima Centauri, way over here, let me clear this. I'll just do an example. I use my straight line tool. So I come down, I'd say, all right, what's the approximate surface temperature? Now, when they say surface temperature, right, obviously means at the surface of the star. Inside the star, millions of degrees. Like our sun is 5,800 Kelvin at the surface. You go inside, it's 20 million, something like that. So Proxima Centauri would have a surface temperature, let's see, this is 2,000, 3,000. Again, you might say 2,800, right? Less than 3,000, 2,800 Kelvin, which puts it in the red category. It's a red star. Barnard star, kind of split the red-orange, so it's a reddish-orange color. Polaris, I'll clear this out. Let's get my straight line tool again. So if I take this and draw straight down, and that's where you got that 6,000, and again, yellow. So Polaris is also a yellow star like we are. Your blue stars you see over here, you've got Spica. Come down from Spica. Spica's looking like, what, about 25,000, right? If this is 20 and this is 30. So your surface temperature of Spica is 25,000, which puts it in the blue category. Luminosity, again, as he was referring to, has to do with brightness. So our sun, again, has just an arbitrary number of 1. If you're looking at Polaris, let's say. So I'll take my straight line tool, take from the plus where Polaris is, and go straight across. Right, you can see he said about 5,000. This is 1,000, 5,000, that's 10,000. So Polaris is about the same temperature as our sun, maybe a slightly hotter, slightly. Same color, yellow, but 5,000 times brighter. Why would it be brighter? More massive, right? He talked about massive over here, smaller over here. See where our sun is? It's kind of middle. That's what I was saying. Our sun isn't the biggest. It isn't the smallest, kind of in between. Average size. Again, with life cycle, they give you the stages. So any of these stars, and he highlighted them in his video, in this whole section, that's a majority of the stars. They're in the main sequence. Main sequence is early stage, so they're not quite halfway yet. That would be our sun. So Alpha Centauri, our sun, Sirius, Barnard's, Proxima, all of these guys would be main sequence. Once we jump off that sequence, main sequence, that's when we're going to get to that 10 billion a year timeline, right? That was that original timeline I showed you. We're going to go from here up here. We're going to go into the Polaris age, Aldebaran, Pollux. All right, we're going to be in the giant stage. That's when we become that red giant. We get cooler because the sun is here, yellow. We'll go this way, up to the right. We become more red and a giant. So we move up to the right, and that's going to be your intermediate stage. The really, really big ones, this is also intermediate, that's your giants will go into the super giants. So some of these guys will go further up on the chart and become super giants. Not us, we're not massive enough. Once we leave that intermediate stage, so we're going from here to here, we're going to leave the intermediate and we're going to go way down here into this section. Then you see it says late stage. So they give you on the chart early stage, intermediate stage, late stage. So this would be right now where we are. Once we start to get older, we become intermediate, and then once we get to the really old part of our life cycle, we'll become late stage. And that's when the outer shell will blow off. We're smaller but hotter, because again, the sun is here currently. We'll go to this side of the chart. We become more of a white color, blue-white, but smaller. We'll become a white dwarf. And that's it. All right, so there's an assignment that goes with this. I think it's like 13 questions. You have to use this chart carefully, so make sure you read this carefully. Go back and watch this video again if something doesn't make sense, and use this chart to help you with that assignment. It's called the ESRT STARS worksheet, I think is what I called it. So use this chart to answer all those questions. And I will talk to you soon. Bye.